Well, in the fifth presentation of this series, we will look into finite state machines, which correspond to chapter 5 of the book. And the expected learning outcomes are that you will be able to explain what finite state machines are used for. You will also be able to differentiate between these two types of finite state machines called Mealy and Moore, and to differentiate between state diagrams and algorithmic state machine charts, or ASM charts, which are representation mechanisms to specify the behavior of finite state machines. And finally, you will be able to translate an ASM chart into a corresponding VHDL description. So you may recall from the previous presentation that finite state machines may be used as the controller in larger circuits known as finite state machines with data path, where they will control other regular sequential circuits that make up what is known as the data path, and a microprocessor architecture may be seen as an example of this type of blocks. So the finite state machine can be used as the controller for the finite state machine with data path. It may also be used for less complex applications, such as sequence detectors or parity detectors or parity generators or other small complexity sequential circuits that exhibit a non-regular state transition. Now, you may recall from a previous presentation that we have looked into a block diagram for the synchronous system, which was similar to this one shown here, with the exception that instead of two, we had only one output logic block. Well, the difference here is that we want to differentiate between those outputs that are a function only of the current state, and these will be called Moore outputs. So Moore outputs will change only when the current state changes, and the case of Mealy outputs. And Mealy outputs, they are a function of the current state, but they are also a function of the external inputs. So when we are in any given state, the Mealy outputs may change if the inputs change. On the contrary, the Moore outputs will only change when the state changes. This is the difference between Mealy and Moore outputs, and most likely any finite state machine may have outputs of both types. If it just has outputs of one of these types, then we may call it a Moore finite state machine or a Mealy finite state machine. Well, the two usual representation mechanisms for finite state machines are state diagrams, seen here on the left, and ASM, or algorithmic state machine charts, seen on the right. In the case of state diagram, we use circles to represent states, and arcs to represent the transitions between the states. In this case, we are looking at a small finite state machine that might be represented as illustrated in the left. In this case, we have two inputs called A and B, and two outputs called Y0 and Y1. And what this state diagram tells us is that we start by state S0, and when we are in state S0, output Y1 takes the value of 1. And the same happens in state S1. And since nothing is said, then in state S2, Y1 will be 0. So this is a Moore output in the case of Y1. On the contrary, in the case of Y0, what the diagram tells us is that if we are in state S0 and inputs A and B take the of 1, then output y0 will take the value of 1. So this is the melee output. Now these state transitions can be read as follows. If we are at state S0, then at the next rising edge of the clock, if input A is 0, then we go again to state S0. On the contrary, if A is 1, then we may go to state S1 if B is 0, or we will go into state S2 if A is 1. So if we are at state S0 and there's a rising edge in the clock and A and B are both 1, then we will go into state S2. From state S2 we will always revert back to state S0 regardless of the values present on the inputs A and B. And in the case of S1 we will either stay there if A is 0, or we will go into state S0 if A is 1. So in this case input B has no relevance for the state transition from S1. Now representing this state diagram as an ASM chart is a very straightforward task, because ASM charts they use ASM blocks to represent states, and ASM blocks are these dotted boxes, and each ASM block will comprise a state box, which is the rectangle at the entrance. It will always be present, and then it may contain, so it is optional, it may contain decision points and conditional output boxes. Conditional output boxes are represented by rectangles with rounded corners. So if we look into state S0, what we will represent in the case of an ASM chart is that the state box will indicate that we have one more output. State boxes actually represent more outputs. So in this case, output y1 will take the value of 1. Then we will have to decide something based on the value of A. If input A, we ask, is input A equal to 1? If this is false, the next state will again be S0, which corresponds to this transition in this state diagram. Now if this is true, then we will ask if input B is 1. And if that is true, then we will assert the melee output y0. And the next state will be S2. In the case of S2, there is nothing inside the state box because the more output is 0. And the next state will always be, the next state will always be S0. So state diagrams and ASM charts are equivalent representations, and actually ASM charts are preferable because when we move up to register transfer level, we can simply indicate register transfer level operations inside the state box or the conditional output boxes. Now in this slide we are looking at a specific example of a finite state machine. Use it as a rising edge detector, and a rising edge detector is a circuit that does what is shown in these waveforms. So there is an input, which in this case is called level, and we want to find out when the input goes up. Now according to our clock sequence here, we can conclude that there has been a rising edge at the input when we read a 0 in one of the rising edges of the clock, and at the next rising edge of the clock we read a 1. When this takes place, then it's because the input has gone high, and so the next clock period we will produce an output, in this case called tick, which will go to 1, and this will indicate that the input has just gone through a rising edge. This is the rising edge detector. So we might represent this behavior in the form of a state diagram by using three states called in this case 0, edge, and 1. We start at state 0 and will remain here while we go on reading zeros at the input. So if we are here and we read a 0, we go to state 0. The next rising edge of the clock also reads a 0 at the input. We remain at state 0. But the next rising edge of the clock, if an input if a 1 is read at the level input, then we move on to state called edge, and the output tick goes to 1, and that is represented here in the waveforms. Now, at the next rising edge, if we continue to read the 1, we will go to another state called 1, where we will remain while the input continues to be 1, and then whenever we read 0 for the first time, we will revert to state 0. Well, the ASM chart for this state diagram is a very straightforward representation, so you shouldn't have any problems by now to represent the ASM chart corresponding to this state diagram. The last learning outcome that we are yet to achieve is how to convert this ASM chart into a VHDL description. This is a very straightforward process, and I will show you how to do so in 2 slides. The first slide is simply use it to tell you that the states that are used to represent the operation of the finite state machine, they are not predefined data type, so we will have to create a new user-defined data type, which we may call state type, which is of the enumerated data type. So an enumerated data type is simply a user-created data type where we indicate all the values that this type may have. In this case, there will only be 3 values called 0, edge, and 1. And if we define a type called state type that comprises these 3 values, then we can define the signals state reg and state next as the state type that we have just created. And by doing so, we will be able to describe the operation of the finite state machine in VHDL. Now, the state register, which you may recall is the block in the middle in this representation, the state reg is represented as usually using the construction that we are already familiar with. So if reset is at 1, then state reg goes to the initial state, which in this case we called 0. Otherwise, if there has been a rising edge in the clock, then state reg takes the value of the state next. And what is left to define is the next state and output logic, which are these blocks here. The next state is defined simply using the case and if sequential statements. So we will build a process comprising case and if statements, and the first thing to call your attention to is that we will define default values for next state and for the output, for the Moore output. And the reason is that very frequently we will see that the next state will be the current state, like in the case of this first decision point being false. Now, if we have defined the next state as the current state, then we won't have to say anything in this case. And likewise, if by default we have said that the output, the Moore output is 0, then we don't have to say it again in this state because it has been predefined by default. So that's what I mean by saving a lot of code lines. If we define the next state to be the current state and the output to be 0 by default, then we don't have to say so whenever we want it to take place. And then it is simply a matter of replicating what we see here. So for case, if we look at the VHDL description, we may say case state reg is when 0 or when edge or when 1, and we list it for all the existing states. And when zero, what we will say is when the current state is zero, then what we have to do is simply a decision point and ask if level is equal to 1, then the next state will be edge. And this is what is defined here. If level is equal to 1, then state next is edge. And, and if, notice that we don't have to say that else if then go to 0 because this has been defined by default. The current state is the next state by default. Then when edge, what we will say is takes the value of 1 and then we will have an if statement to define the next state. And here we see when edge is the current state, then tick takes the value of 1, and then if level is equal to 1, then state next will be 1, else state next will be 0. And the same will take place for state 1. So coding the ASM chart is a very straightforward task indeed, and you just have to replicate what you see in the ASM chart using the case and if sequential statements. I strongly recommend that you go to page 115 and see, and in this case the code is represented before the ASM chart, and so you can use this listing in the project navigator, and you can create a test bench once again and watch the operation of the rising edge detector in practice. I strongly recommend that you do it because that will be the best way to fully understand how this works.